Types of reactions. You can read the preamble here. First type of reaction we're going to look at is synthesis. It's when two separate materials combine to form one. This is not anything new. This is simply looking at our balanced equations and seeing a pattern to them. So scandium and phosphorus are a single element, and they merge to form a single compound. So we have two separate entities become one over here. You can be distracted from this on more complicated examples. So for example, here we have pairs of elements. This will cause confusion for some people, but if you look at it, it's still one thing plus another thing becomes one. The key is there's a plus sign in between and the plus sign vanishes. Don't let all the little numbers throw you. If we balance them, this one was already balanced, but if I balance this one, you get this equation, and it starts to look more messy, but there's a plus sign here, and there isn't one there. This guy here gets even worse. If I write it in this form and we go to balance, first thing we see is the sodiums are out of balance, so we fix that. And we see the nitrogens are out of balance, and we fix that. Oops, when we fix the nitrogens, we just screwed up the sodiums. So we come back in, fix the sodium. Changing a number once is perfectly normal in chemistry. Changing it twice can happen. If you have to change it a third time and it's still not balanced, come and see me. You've made a mistake somewhere. These chemical reactions just aren't that common. Literally, this is in some of your electronics. This doesn't really happen in any meaningful way, turning hydrogen to methane. And this reaction is of intellectual curiosity. There's no uses for it at all that I can find. But these three, two of them are quite interesting. Mercury sulfide was a material called cinnabar. And it's a beautiful red and was used for thousands of years for the dye vermilion. Unfortunately, mercury sulfide is toxic, contains mercury in it. People love to play with it because if you heated this red mineral, it would break apart into mercury and sulfur. So you'd get the poison liquid metal mercury out and then sulfur gas, which wouldn't be great to inhale. It broke apart, and breaking apart is called divorce or decomposition. We could take this and run it the other way as well. So people used to love to play this game. They'd heat mercury sulfide in a jar. It would turn to mercury from a red powder to mercury and sulfur, keep heating it for a while, and it would run backwards again. And they just thought, oh, it's going around and around. And then they made really weird connections to eternal life and all this kind of stuff. Boiling mercury in your lab is just not a good thing. Coloring your clothing with this stuff, no. This one is really cool though. This is called sodium trinitride, or they give it a nickname sodium azide, and it's what's in the airbags of your car. When this stuff decomposes, blammo, it forms sodium and nitrogen gas, and a lot of it at that. Okay, a huge quantity of nitrogen gas comes out. So if we balance it, it's starting to look nasty, but it's still one thing becomes several. That's the definition of decomposition. This is an explosive reaction that produces a huge amount of nitrogen gas and powers the airbags of your car. They're looking for a replacement because if the airbag chemicals get really old, sometimes the sodium doesn't get absorbed and people get burned from it when the airbag goes off. This one you see every day. A big molecule called carbonic acid falls apart into water and CO2. That's what happens when you open a pop. The carbonic acid is unstable and it just spontaneously falls apart, releasing CO2 bubbles, which is what's in soda pop. The acid makes the soda pop a bit edgy, a bit sour, and by the time the pop goes flat, it tastes sickly sweet. Single displacement is a guy stealing someone else's girlfriend. So here's a happy couple, and guy C shows up and he steals the girl. You can reverse the sexual example at your convenience. for whatever mode you want to think about. Let's look at it in real life. Hydrogen chloride and magnesium. Now magnesium's got the girl and hydrogen is single. That's why we call it single displacement. One guy chased away another guy. Looks okay right now till we finish it. So that's the theft that's going to happen. Magnesium is going to take chlorine. But let's balance this equation. We get that. And then we know hydrogens can't go out by themselves. So we have that. Now we have an imbalance. We fix the imbalance. And we have this equation. Now it looks nasty. It's hard to see that it's a single displacement. So you ignore the numbers and pay attention to what's happening. Magnesium went in and stole chlorine. Magnesium was single. Now hydrogen is single. That's the key. All this other gobbledygook is in your way. Silver meets hydrogen sulfide, which forms silver sulfide and hydrogen gas. So silver punched the lights out of hydrogen and stole sulfur. And when silver does that, it begins to tarnish. And this rotten eggs gas leaking into a building or building up over time can lead to one color of silver tarnish. Most silver tarnish is black because fortunately hydrogen sulfide is not common in our environment. It's that rotten eggs odor that keeps coming from the sewage treatment plant. This one is a real cool reaction I'm going to show you. If you mix aluminum metal with iron oxide, iron rust, and set it on fire, the aluminum will steal the oxygen and release the iron. And it's like a bomb going off. It's this huge incendiary flare of molten metals exchanging places, and you are left with glowing heaps of iron. It's a phenomenal way of sort of like welding with an explosion. You can also use it to destroy things like tanks and enemy artillery quite effectively. So we got to definitely look at the thermite reaction. When I balance them, they look a bit nastier. The last kind of reaction is double displacement. These two are going to switch partners right here. So no one's left unhappy. So chlorine and fluorine will just switch places. And this one's lovely because there's no balancing required. Now, does it actually happen in real life? I don't know if the reaction would happen, but it could, as in the fact that we can see it, can assemble this way. We just don't know if it would actually take place. So this one is more typical. And you can see how messy it looks. Chlorine, nitrogen, and they switch. And this can trip you up. But simplify it. Pay no attention to the numbers. Now look at it. It's just as easy as this one. Chlorine and nitrogen switch places. When you put it all together, it looks horrible. But if you just in your mind ignore all these numbers, you can see what's going on quite easily. Chlorine and nitrogen switch places. This one is used in some water softeners, not in Orangeville. This gets a bit more complicated yet again. Magnesium is married to this cluster called carbonate, highlighted in blue, and calcium is married to this cluster called hydroxide. If you look over here, the clusters have simply switched places. So you can do double displacement with a cluster of things. What clusters are we going to look at? Hydroxide. That's the only one we need to worry about. But you can see that I've highlighted it in blue. It should be pretty obvious what switch places. The carbonate iron is called chalk when it's calcium carbonate, and it switched places with the hydroxide. And hydroxide is what makes Drano. The double displacement reaction I've already done with you is the making of stannous fluoride, the fluoride in tin. And what you can see is the oxygen and the F switch places, and this turns tin rust and a deadly acid into toothpaste and water. And you better get that balancing right. If you accidentally put in 4 scoops of hydrogen fluoride, goodbye to your teeth, your tongue, your esophagus, and probably your lips too. And that's the one I would like you to be able to do because it's a definite, realistic, real-world reaction.